Hello, my dear students. Let me start the syllabus. I mean the topic. Before I start the syllabus, I want to recall some important definitions related to the computational linear algebra. The first point, I mean the key points related to the computational linear algebra is algebra. A set which is both a vector space, and you know the definition of vector space. A set which is both vector space as well as a ring is called as algebra. Let me repeat. A set A, of course it is non-empty, which is both vector space as well as a ring is called as algebra. If and only if alpha of AB is equal to alpha of A of alpha B, or we may write it as alpha A of B for all AB belongs to a non-empty set A. Second point, if the homomorphism which is both 1 and onto, a homomorphism which is both 1 and onto is called algebra of isomorphism. A set of all homomorphism of V into V is denoted by this notation homomorphism of V into V. What V stands for? V stands for here the algebra. Okay. Now, a homomorphism of V into V is the algebra and is denoted by the notation A of V. In other words, A of V containing n elements, that is An of V. Algebra of a linear transformation on V is denoted by, and you know the definition of linear transformation that we have studied in UG. Algebra of a linear transformation on V is denoted by A of V or homomorphism of V into V. The next point, the mapping in a homomorphism of V into V, the mapping is from A to A, that means V to V, is said to be algebra of homomorphism if it preserves vector addition property as well as scalar multiplication of vector property. In the UG, we used to write T of V1 plus V2. Here the notations are different. That means the presentation is different. V1 plus V2 of V is equal to V1T plus V2T. That means V1T of V1, T of what? A2. I hope you got it. The next one, alpha V of T is equal to alpha of Vt, where alpha is a scalar, that means belongs to F. V is a vector, that means belongs to V. The next point, where V and W are the vectors, V W of T can be written as V dot, that is Vt dot Wt. That means image of V under T and image of W under T. And V and W are the members of vector space V. The next point, the next definition is what? Direct sum. If W1 and W2, if W1 and W2 are the two vectors subspace, and you know the definition of subspace, if W1 and W2 be the two subspace of a vector space over a field F, then we denote the direct sum of two vector subspace as W1 plus W2, that is sum of two subspace is a set containing the elements of the form or containing the vectors of the type W1 plus W2, where W1 belongs to subspace W1 and the element W2 belongs to the subspace W2, and we denote it by this notation. W1 plus, we write that plus inside the circle that indicates the direct sum of two subspace W1 and W2. Okay. The next definition, dual space. Now the question arises, what is the meaning of dual space? Let V be a vector space over a field F. Any linear transformation means satisfying vector addition and scalar multiplication of vector property. We call it as linear transformation of V into F is called as linear functional on V. The vector space homomorphism of vector into scalar over a field F consisting of all linear functional on V is called as dual of a vector space V, and it is denoted by V star. A linear transformation U into V is denoted by what? Is denoted by homomorphism of what? U to V over a field F. Next definition. Let V be a vector space over a field F and we denote it by V of F. Be a finite dimensional vector space with unit elements E1, E2 and so on here. And it's ordered, they are what? They are the unit vectors. Unit vectors means definitely they are related to what? The basis. If the product of two unit vector space, if the product of two unit vectors is 1 when I equal to j and is equal to 0 if I is not equal to j, and we denote it by the notation delta ij, and we call it as Kronecker delta, is called as dual of a basis or simply dual basis of what? V star. Next definition, double dual. For a given vector space V, the dual of V is denoted by the notation V star. It means homomorphism of a vector space V into scalar F. And we denote the double dual by the notation V star star. That means V double star. And what is this? This is a mapping from V star to what? F. The double dual consists of all linear functional from what? Dual space, that is V star to what? F. Remember one point. Dimension of double dual, that is V double star, is same as the dimension of dual space, that is V star, and it is same as dimension of a vector space. That means dimension of vector space is equal to dimension of dual space, and it is denoted by V star, and this is same as dimension of double dual, that is V double star. One important theorem. Let V be a vector space over F. Then the double dual, that means V double star of a vector space V, this word is very important, is isomorphic to V. Whenever we see the word isomorphic, we denote it by this notation. V double star is equal to, not equal to, is isomorphic to what? The vector space V. This we have to prove. Let me prove this theorem. Very simple proof and interesting also. Let V be vector space over F. Let me take an element. V0 is an element of vector space V, and a linear functional F belongs to dual space, that is V star. Let us, to prove the isomorphic condition, we need a mapping. We have to show that that mapping is what? Homomorphic, and it is 1 1 and onto. Let us define a mapping, I mean the function T V naught from dual space, that is V star to F. Whenever we have a mapping, the condition should be there. The condition is what? T V naught of F is equal to F V naught. Using this condition, we have to show that it is homomorphic, that means same as linear, then 1 1 and onto. Let me show T V naught is linear. To prove or to verify the linearity, we have to check whether it is a vector addition or not. If it is vector addition if the vector addition property holds good, then we have to think of what? Scalar multiplication of vector property. Okay. Let me consider two functions. F1 and F2 belongs to V star, that means dual space, and alpha beta are the scalars. Let me take the first property, I mean the linearity condition. T V naught of alpha F1 plus beta F2 can be written as, using the condition, alpha F1 plus beta F2 of V naught. Again, rearranging, this can be written as alpha dot F1 of V naught plus beta dot F2 of V naught. Again, using the hypothesis, I mean the condition of the mapping, this can be rewritten as, or this can be written as alpha dot, alpha is a scalar, TV naught of F1 plus beta dot TV naught of F2. Now, let me take a new mapping. The new mapping is from I will call the new mapping as phi. Phi is a mapping from V to V double star, that means double dual, defined by this condition, that is phi of V equal to TV. I mean same, that is TV. Okay. First, whenever we see the word new mapping, I said number of times, we have to check whether this mapping works or not. That means we have to see whether the mapping is well defined or not. To check whether the mapping is well defined or not, the easy way is what? To verify whether the 1 1 property holds good or not. If the 1 1 property holds good, that indicates the mapping is well defined. That means we can move forward. If V1 equal to V2, then taking the image of these two, image of V1 under F, that is FV1, image of V2 under F, that is FV2. Using the given condition, this can be written as TV1 of F and right hand side TV2 of F. This is same as writing V1 TV1. TV1 is equal to TV2. Again, this can be rewritten as phi of V1 equal to phi of V2. That means if the elements are equal, the images are also equal. That means 1 1 property 100% holds good. That indicates the mapping is excellent. That means it is well defined. Again, let me rewrite systematically. Phi is, the new mapping is 1 1. Since it is well defined, that means we have to check 1 1 onto and what? Enough. Since it is well defined, 100% it is 1 1, but we have to write systematically. Here we have taken, if the elements are equal, images are equal. Now to verify 1 1, let me take if the images are equal, whether the elements are equal or not. If phi of V1 equal to phi of V2, then using the given condition, we can prove that V1 equal to V2. What indicates phi is 1 1? I said number of times, the condition of the mapping itself is onto. Clearly the mapping is onto. Since it is 1 1, and onto, and the linearity condition holds good, that indicates the mapping is homomorphism. Now, the next point we have to complete by taking the last part, which is we have to show that whether it homomorphism property holds good or not. If it holds good, that means it is isomorphic. Phi of alpha u plus beta v can be written as T of alpha u plus beta v of f. This can be written as f of alpha u plus beta v. Again, rewriting alpha dot f of u plus beta dot f of v. Again, this can be rewritten as alpha dot tu of f plus beta dot tv of f. Again, using the condition of the mapping, we can rewrite it as alpha dot phi of u plus beta dot phi of v. That indicates what? This indicates the mapping is homomorphism. Since it is homomorphic, 1 1 onto, clearly the new mapping is isomorphic. That means the double dual, that is V double star, is isomorphic to vector space V. Now let me take a beautiful and interesting lemma related to the algebra. Now the question arises, what is the meaning of algebra? If a non-empty set A satisfy what? The vector space condition as well as ring properties, we call it as what? Algebra. If A is an algebra with unit element over a field F, then A is isomorphic to subalgebra of A of V for some vector space over F. Let me prove this lemma. The proof of this lemma is very simple and beautiful. Since A is an algebra, that means the non-empty set A is an algebra, that means it satisfies vector space property as well as the ring property, the conditions of ring. Since A is an algebra over F, hence it is a vector space, because since A is algebra, therefore it is a vector space. What do I do now? I replace the vector space V by a non-empty set A. To prove the result, it is necessary to change V by what? A. Let A belongs to A. If A is an element of A, let me take the mapping. T is a mapping from algebra A into algebra A. Whenever we have a mapping, the condition is important. Here the condition is what? V dot TA is equal to VA for all V belongs to a non-empty set A. What do we have to show? We have to show that this mapping is linear. Linear means it preserves vector addition property as well as scalar multiplication of vector. Okay, let me take vector addition property. Here, actually what we see, in the UG used to see V T of U plus V, but here the presentation is different. Let me consider V1 plus V2 of TA because the mapping is TA. Okay, that means image of V1 and V2, that is image of sum of two elements, that is V1 and V2, can be written as V1 plus V2 of A. Again, this can be written as V1A plus V2A. Again, this can be written as V1 dot TA plus V2 dot TA. This preserves what? Vector addition property. Now I'll take scalar multiplication of vector property. That means we have to multiply a scalar by a vector. Alpha dot V, that is alpha V, where alpha is a scalar, V is a vector space, V is an element of a vector space V. That means V belongs to what? Capital V. Alpha dot V of TA can be written as alpha V of A. Rearranging the terms, since it is a vector, since it is a and that means since it is an algebra, therefore the vector space property holds good. So clearly the new mapping is linear. Now let us form another mapping, say from algebra A into subalgebra A of V, defined by this condition, that is Azi equal to Ta. Again, clearly the new mapping is homomorphism because the property is very simple, and what it indicates, if Ta and Tb are linear, then their sum T alpha A plus beta B can be written as alpha dot Ta plus beta dot Tb. This indicates clearly it is a vector space of V into A of V. Now we have to verify the another condition of what? Linear transformation, that is scalar multiplication of vector. If if A and B are the elements of A, then V dot T AB can be written as V of AB, and rearranging or grouping VA of B, and this can be written as VTA of B. Again, this can be rewritten as VTA dot TB, that is VTA dot TB. Again, taking V outside, V dot Ta dot Tb. Since A is common between these two, I mean left hand side as well, we can see V here also. Here also, ignore that T, that means element V. This can be written as TAB is equal to Ta dot Tb, or in other words, AB of Z equal to Az dot Bz. What it indicates, clearly the new mapping is homomorphism. Again, to see whether it is isomorphic or not, I have to check two more conditions, that is 1 1 and onto. Clearly this mapping is 1 1. As said number of times, the mapping itself, I mean the condition of mapping itself shows that it is onto. Since it is onto, therefore it is isomorphic. This completes the proof of what? The beautiful lemma. Is it okay? Thank you.